Well, hello. Welcome to Physics with Mr. K. We're going to be talking today about forces, free body diagrams that we use to analyze forces, common forces such as weight, normal force, which is another word for compression, and friction. We're going to look at two different kinds of friction, actually. Friction when something is sitting still, and friction when something is moving. Call them static and kinetic friction. So we got weight, normal force, static friction, and kinetic friction. We're going to look at all of those today with the help of this little experimental setup that I have here and a free body diagram that I'm going to put up on this board. First of all, what have I got down here? Well, is a wooden block, just an ordinary wooden block. It's got a little hook on one end so that I can split with the string. I have another one sitting here on the table. So I've already loaded this up with all kind of assorted weights so that the total mass sitting on this tabletop is 3.00 kilograms, as close as I could get it to exactly 3 kilograms. Now, how can I represent what's going on with this block using a free body diagram? Well, I've got my XY axis here as a help, and I'm going to start drawing stuff. What do I know about this block? I know that gravity is pulling it down. I can actually put a number on that in a second. Let's just draw an arrow first. Here is a big dot that represents the block. That's the body in this. It's a free body diagram because I am mentally freeing something, body, the block in this case, with all the weights on top of it as a system. And I'm making a diagram of all of the forces on it. We've discussed already the principle here. For translational motion, an object acts as if all of the mass were at the center. So I don't need to draw a fancy picture of the object. I can just draw a dot representing the center of mass of the object, and I can draw arrows for all of the forces that are applied to that object. We already talked about the first one, weight, which of course is pulling straight down toward the center of the earth. So I'm going to draw an arrow to represent it. Always on a free body diagram, you want to put some kind of a label. So I'm going to put F for force with a subscript G for gravity. The gravity due to the earth, to be specific. Now, what else do I know about this object? Well, I can clearly look at it and see that it's not accelerating. It's not even moving, let alone accelerating. So it must be, by Newton's second law, that all of the forces add up to zero. Let me write Newton's second law, solved for A. Acceleration is net force divided by the mass. It needs to be accelerated. Now, this body's mass is 3, but it's not accelerating, so I know the left and the right side of this equation have to both be 0. We call this equilibrium. This object is in equilibrium. The net force is 0. Those two things mean the same thing. 0 net force, 0 acceleration, equilibrium. Well, gravity's pulling down. If the net force on this thing is 0, it must be that something else is pushing up to cancel that out. And that something else is called the normal force from the tabletop. The tabletop is pushing up just exactly strong enough to support the weight. Let me draw an arrow to represent that. Now, used a little smartboard trick there to make sure I drew them exactly the same length because they're supposed to be the same strength. One is positive, up, positive y direction. The other is negative, down, negative y direction. Together, they must be canceling out because this object is not accelerating. Of course, I just put a vector arrow to represent a force. Always in free body diagrams, I have to make sure that I put a label on that. It's a force. What kind of force is it? N for normal. You look in the dictionary after the usual definitions of normal, somewhere down the list, there is the geometry definition of normal, which means perpendicular. Call this a normal force because it acts perpendicular to the tabletop. It's pushing straight up. It doesn't always push straight up. If this tabletop were, for example, tilted, then it would still push perpendicular to the surface, but that would no longer be straight up. We'll deal with that situation on a later day. So I know these two guys have to equal each other because in the y direction, there's no acceleration. The forces have to cancel. Okay. Are there any other forces on this thing? No. There's nothing to push it in any other direction. These two must cancel out with zero acceleration. So what if we applied a force? I have a string that is connected to the block, and I'm going to pull it. If I pull just a little bit, nothing happens. What's going on? There must be something that's keeping it from moving. If I'm pulling and it's not accelerating, that equation there says that if there's a force, it ought to accelerate, and yet it's not accelerating. It must be that even though I'm pulling that way, something must be pulling the other way to cancel it out, to keep the object in equilibrium. And that something is friction. In particular, because the object is not moving, because it's stationary, because it's staying right there. You know, if you stay stationary at the station next to the stadium, I mean, you might be an obstacle because your status is stationary. Static is the word. This is called static friction. Friction when an object is not moving. Static friction is something you can't put an exact equation on because it could be any of a number of values. If I don't pull at all, there's no need for friction to resist the sliding because there's nothing making it slide. Remember the definitions of our forces. The normal force is a compression. It resists squeezing. If this tabletop were a pillow, you would see a dent. This weight is pressing down and the tabletop is resisting that by pushing back up. If friction resists sliding. If I pull this sideways, then friction is resisting by pulling the other way. Friction is pulling that way. I'm pulling this way, friction is pulling that way. Up to a certain point, the friction is strong enough to cancel my pull out, but there's a limit. If I keep pulling hard enough, there you go. Eventually, something's going to give, and the object is going to start to move. So static friction could be zero, could be any number, whatever is needed to keep the object sitting still until you get to that maximum limit, and then the force is just too strong, and boom, the object moves. That is called the limit of static friction, the maximum possible static friction. Let me add those forces to my diagram. I'm pulling that way. Actually, I'm pulling on a string. So actually, it's a tension. I'm trying to stretch the string. The string is resisting the tension. What's pulling the other way that's keeping this from moving? Static friction. The standard notation for friction is sort of a script F. And I'm going to put a little S under there, the subscript meaning static friction. Write that. So what this diagram is saying is that in the y direction, vertically, this normal force is canceling out the weight on the object. That's why there's no acceleration in the vertical direction. And this is also saying my pull that way is being canceled out with some static friction pulling the other way, again, canceling out so that the object doesn't accelerate as long as we stay below that limit. What happens if we go over the limit? Well, we have a very interesting little experiment we're going to do based on that, and I'm going to show that to you in just a moment. Let's talk about the experiment you are about to see. The purpose is to investigate the question, how does friction depend on normal force? In this experiment, a wooden block was placed on a horizontal surface. A string was attached to the block. By pulling on the string, a tension was applied to the block, pulling in the horizontal direction. A force meter was used to measure the tension in the string. The point of the experiment was to answer the question, what is the mathematical relationship between the friction and the normal force between the block and the surface? The aim was to answer this question for two types of friction: static friction, friction when there is no motion, and kinetic friction, friction when the block is sliding, that is, when the contact surfaces are moving relative to each other. In the setup below, if you pull the block with too small a force, it will not slide because static friction will hold it still. But there is a limit to how strong static friction can be. Pull the string hard enough and the block will start to move. One part of the experiment was to examine this limit by measuring the maximum static friction for a given amount of mass on the block. Once the block begins to move, the block will slide at a constant velocity with zero acceleration if the tension pulling to the right equals the kinetic friction that resists the motion by pulling to the left. A second part of the experiment was to measure this kinetic friction for a given amount of mass on the block. In different trials, different amounts of mass were placed on the block. Varying the added mass varies the total weight, and thus varies the normal force between the block and the surface. This normal force equals the total weight. Normal force equals mass times g. For each amount of added mass, the maximum static friction was measured by noting the tension in the string needed to get the block to budge. Also, for each amount of added mass, the kinetic friction was measured by noting the tension required to drag the block at a constant velocity. For each trial, a certain amount of mass was added to the block. The tension in the string was increased until the block moved. The tension reaches its highest value just as the block budges. Measuring this peak tension gives a value for the strength of the maximum static friction, as the two are equal at the instant just before the block budges. After motion began, the block was towed at a constant speed. At a constant velocity, with zero acceleration, the net force was again zero as the pull of the tension was balanced by the kinetic friction. Thus, measuring the tension gives a value for the strength of the kinetic friction. A force meter was used to measure the tension, thus giving values for the maximum static friction and kinetic friction. Here we see a free body diagram for the situation in this experiment. The diagram represents the block and the forces upon it. With no acceleration in the vertical direction, the normal force between the block and the surface must equal the block's weight. With no acceleration in the horizontal direction, the tension in the string must equal the friction. For each amount of added mass, a trial was conducted by dragging the block with the string. Each trial resulted in a graph of force versus time from which values of maximum static friction and kinetic friction can be found. The next slide shows a typical force graph for one trial. For each trial, the normal force between the block and the surface can be found from the total mass. The normal force equals the weight, which equals mass times g. This chart shows the result of one trial for one particular value of mass. This is produced by a force meter that is connected to the string used to pull on the block. The force meter then connected to the software that produced this graph. It shows how the force, the tension in the string, varied over time as the block was pulled. At first, there's no tension in the string, and then at approximately 1 second, the force begins to increase, the tension increasing as the block is pulled, but the block is still not moving. It's right about at 2 seconds when finally the maximum static friction is exceeded and the block begins to move. In the region between approximately 2.5 and 3.5 seconds, the block was dragged at a constant velocity. This is going to be used to measure the kinetic friction. We can use this slide to see how to extract data from the graph. First of all, the mass is listed at the top. This mass can be used to calculate the normal force simply by multiplying the mass times g. The maximum static friction is the peak of the graph. In this particular example, that happens at approximately 2 seconds. You can see the value of the maximum friction by looking for the max value in the appropriate statistics box. In this case, the maximum value was 0.905 newtons. Then there is the plateau where the block was dragged at a constant velocity. The mean value of the friction during this region is the kinetic friction of the block, between the block and the surface. In this example, it is 0.541 newtons. This slide can show what to do with the data once you have obtained it from the graph, as shown on the previous slide. I suggest you make a data table similar to what you see on the right-hand side. 4 columns, one for mass in kilograms, then normal force in newtons, maximum static friction in newtons, and kinetic friction in newtons. Each row representing the results from a single trial. The previous slide showed results from a trial with a mass of 234 grams, which is 0.234 kilograms. This was the smallest mass used in the experiment, the mass of the block alone with no added mass on top. The normal force can be calculated, m times g, as 2.29 newtons. The peak of the graph, the max value in the first statistics box, was 0.905 newtons. This was the maximum static friction for that mass. The mean value of the plateau portion of the graph, as shown in the second statistics box, was 0.541 newtons. This was the kinetic friction for this mass. These values complete one row on the data table. The assignment. Please make a graph that shows the relationship between friction and normal force. The data to be plotted will come from the table of data that you assemble from graphs, each showing the result from one trial with one particular value of mass. The graphs are included in a PDF document available to Mr. K's students in their Canvas course. The graphs are also shown at the end of this video. Normal force should be plotted on the horizontal axis with friction on the vertical axis. We'll use this graph to discover the relationship between friction and normal force. This slide should show you some idea of what the graph is supposed to be like. We're going to put normal force at the bottom on the horizontal axis. Make sure that you plot normal force, not mass. And friction goes on the vertical axis. You can use the same scale for both kinetic and static friction. They're both going to fit within the same range. On the right, you see a suggestion for how to make a data table to keep track of all of the data that are going to go into this plot. For this assignment, you may make a paper graph. If so, please use graph paper, not ordinary lined notebook paper. And I suggest you use pencil, unless you are one of those perfect people who never makes a mistake, like me. Well, I thought I made a mistake once, but it turned out I was wrong. Anyway, you may also use software to make a graph. There are a number of good options for this. For one, you can download a free copy of Vernier's graphical analysis. You can also make a graph online at a number of sites. Here are two good ones, Desmos and Plotly's Chart Studio, both of which are free. Graphical analysis and Desmos are also available as cell phone apps. Please try to complete your graph by our next class. We will discuss how to interpret the graph then. But see if you can anticipate that conversation. The goal will be to find two functions, max static friction as a function of normal force and kinetic friction also as a function of normal force. Once you have the points plotted, ask yourself, what type of function are you seeing? Can you express each function as an equation? If so, do so and bring your result to class. At this point, we'll return to the live portion of the video where you can see how the data is obtained. Okay, here we are. I changed the screen. What I have here is a little meter that actually measures force. When you pull on this thing, it'll actually, just if you look at the number there in the bottom left corner. Right now it's, yeah, there goes 0. But if I pull on this, it registers that I'm pulling. And actually, if I push in on it, it would register negative numbers to show that I'm pushing in, because it measures in both directions. I'm going to use this to measure how hard I'm pulling on this block here in order to get it to budge. Because until I get it to budge, the static friction is going to build up and build up and build up, and it's going to be strong enough to keep that thing in equilibrium, keep it from moving. But at a certain point, it's going to give way. And you're going to see that right up here on the graph. Here we go. Pulling more. Ah, there it gave way. Something budged right there at. And this software is great. Somewhere in this region here, between here and there, tell me the statistics. Tell me the peak. This is for this region right here. It's telling me that the maximum force was 10.8 newtons. So that tells me that for this amount of weight, the maximum possible amount of static friction was 10.8 newtons. More than that, and it moves. Well, what happens after it moves? Notice that the friction jumps down. This level here is clearly less. Not only is this less, but it's kind of even. It's a bit jumpy there, but it's pretty much a plateau. Don't worry about those little jiggles. To use one of my old jokes, everything about friction is a rough estimate. This is pretty much staying the same here as the object was moving. Notice that that's less than this peak. So we have here static friction building up, up, up. Static friction can be anything from 0 up to some limit. In this case, the limit was 10.8 newtons. As soon as we exceeded that, the object moved. And at that point, the friction dropped. In this situation here, we had less friction while the object was moving. We call that kinetic friction. Kinetic being an adjective, it means moving. This is right there at the peak, and this is the kinetic friction. Which clearly is less than the maximum static. By the way, you might be wondering how the speed of the block, see if that makes a difference. Oddly, it really doesn't. As long as you're dragging the block at a steady velocity, it won't really matter whether you're pulling, whether it's moving fast or it's moving slow. What matters is the block accelerating or not? I'm going to try second trial here, and I'm going to try to drag the block at different speeds so you can see what happens. There, it just budged. Now I'm dragging slowly. Now I'm going to drag faster. Now I'm going to drag slowly again. See what we have. Here is the peak. Yeah, this time it was actually a little bit higher. It was 11.7. But like I said, everything with friction is a rough estimate. What about these three regions here? You notice the plateau is about the same for all of these guys, right about 7 newtons. This is when I pulled slowly. This is when I pulled faster. And this is when I pulled slowly again. The peaks, the jumpiness here is when the block was slowing down or speeding up. But the moments when I was pulling it along at a constant velocity, pretty much a steady level. Kinetic friction, it doesn't matter if something is moving at a slow constant velocity or a fast constant velocity. The kinetic friction is going to be roughly the same. And the kinetic friction is always going to be less than the maximum static friction. I used the word equilibrium earlier to refer to the situation where the block was not moving. I could go further and use another word and call that static equilibrium. Because not only is the net force on it 0, but it's also stationary. It's not moving. It's static again. What do we have here in these situations? These are situations where the velocity was constant. If the velocity is constant, the acceleration is 0. And when the acceleration is 0, it must be true that the net force is 0. These are situations where my pull was exactly canceled out by kinetic friction. Even though the block was moving, it's still in equilibrium because the net force is 0. It's not accelerating. So looking back at my diagram, in the situation where I was dragging the block at a constant velocity, we didn't have static. And in those cases, the force, the tension force that I was pulling that way was exactly canceled out the kinetic friction pulling the other way. What do you think would happen if I loaded this thing up with even more weight? What if I got rid of all of these guys? And throw on a couple really heavy books. Now there's a whole lot of weight pressing down on this block. You think the friction is going to be the same? What does your common sense tell you? Well, here's a very fast little informal experiment you can do right now that will convince yourself what's going to happen here. Take your hands and put them together like this. Let's say you're somewhere up north and it's really cold and you need to warm your hands, so you're going to do this. Just barely press your hands together and you'll find it's very easy to slide your hands. But press your hands more firmly together and it gets more difficult to move. The stronger the compression, the more friction. The stronger the normal force from this tabletop, the more the block and the tabletop are pushed together, then the more friction you're going to get. Let's repeat this little experiment with this extra weight. The last time we tried this, the maximum static friction was around 11 newtons, and the kinetic friction was around 7. Go, collecting data now. Building up the tension, and there it goes. Now I'm going to drag it at a constant speed and let it go. And let's see what we've got. Wow, we're way off the charts here. We're way up here, just over 20. We got a much higher amount of friction. The maximum limit was now 20.8, almost double what it was before. And the kinetic friction, again, we have kind of a plateau here where I was dragging the block at a constant velocity. That was about a mean value of about 19 newtons. Again, less than the static friction, but more than the kinetic friction was the first time we did this. Well, this is a really interesting lab. What exactly is this relationship? We know that the harder this weight pushes down on the table, the harder the table pushes back up to support it, and that compression force increases the amount of friction. But what kind of relationship is it? Maybe it's the simplest kind of relationship and we're going to get a linear graph, or maybe it will be some kind of a curve, some other sort of function. It would be interesting to find out. So that's exactly what we're going to do. We're going to take enough data with enough different amounts of weight that we can make a graph to compare how strong the normal force is to how strong friction force is, so we can see what's really going on here and what kind of a function relates to it. Thank you very much.
Now we begin with the slides that show the results from each trial. If the block were not touching the surface, there would be no normal force, and likewise there would be no friction. Therefore, your first data point is at the origin. 0 normal force, 0 friction. You can determine other data points from the graphs on the following slides.